So, okay, previously we talked about the wall, which is equal to F multiplied by the distance, which is X, which is F X cosine theta between F and X. Also, we talk about kinetic energy, which is half mv squared. Any question about them? Both of them are energies because the first one we measure it by joules, and the second one is also by joules. And the energy, it is the property of a system. If that system can do that work or act by a force on something. If it is a moving object and hit any other object, then these objects will interact by a force. This is kinetic energy transferred to a work. And the force acting on this second object. Today we will talk about a new kind of energy, which is a potential energy. These are two kinds, are simple as we see, and also the potential energy. Now, and we see also from before that the word can be stored in a kinetic energy as a change in kinetic energy, which is kinetic energy finally minus kinetic energy initially. What is the relation now between the word and the potential energy? If we have an object and this object for two experiments, initially the object at altitude at height y2, secondly at height y1. What if we need to move the object from point to point? Not you, it is the gravity. We are talking about the potential energy due gravity. Now, if we lift this object to move down, then there is a force acting on that object, which is the weight. And the displacement is downward. So if we need to compute the wall, it is equal to the force multiplied by delta W, delta Y, as dot or scalar product. The force is the weight, which is equal to mg downward And delta y is also downward. Let us put it delta y. Or delta y is equal to y1 minus y2. This is y initially, this is y finally. y1 minus y2. And cosine theta between them. How much theta between y and weight, the force? Zero, yes. Both of them are the same direction, downward. The weight downward, the movement is also downward. So cosine 0. This is equal to 1. The second experiment, the work due gravity. We have that change in position is upward, but the weight is downward. So if we need to compute that work, it will be equal the weight downward, which is mg downward, multiplied by delta y, which is y2 minus y1, right? y2 minus y1. But this is upward, as we see. So cosine theta, how much theta here? Yeah, it is 2 pi or 108. Any question about that? Cosine theta in this case is minus 1. This is minus 1. This is positive 1. Now, if we need to see the work in the first case, the work in the first case, mg y1 minus y2. y1 minus mg y2. This is the work. Due gravity. G small or G capital as you like. The second case, the work is equal to, we have mg y1 y2 and mg y2 minus mg y1. All of them multiplied by minus 1, right? Then this will be in negative sign, and this will be in positive sign. So if we need to reorder it, it will be mg y1 minus mg y2. This is weight due gravity. As we see, the weight is that work due gravity, not weight. I'm sorry. The work due gravity, it is not equal. Look at the kinetic energy. The work is equal to 1 over 2 m v2 squared minus half m v1 squared. It is v2 minus v1. This is delta, right? But in this case, we have the opposite direction or the opposite sign. It is y1 minus y2. y1 minus y2. It is not like that kinetic energy. Now, okay. When we compute this term, we define it as kinetic energy. Now we have new terms. This term, and these are the same also. This term, this is work. Previously, we see that the work converted to kinetic energy. Now we have the work converted to a new kind of energy. This energy, we can call it potential energy. This potential energy is due gravity. We will see later that we have many types of potential energy. We have chemical potential energy, photoelectric potential energy, we have biological potential energy, we have spring potential energy, and so on, and nuclear also potential energy. But we have now, until now, just one type of kinetic energy. In the future, we will see that other type, which is rotational kinetic energy, like this. This is rotational kinetic energy. Now we have a new type of energy, which is potential energy. And as we see, the work will convert to a change in potential energy, and potential energy will be sampled by U. Different books, you will see it V, for example, or P. But we will take it as U. It is a change in potential energy, but with negative sign. Because we have Y1 minus Y2, which is equal to U1 minus U2, not U2 minus U1. Right? Now we are just defining new things we need to learn about. Later we will do some examples. It will be more simple. Okay. I'll keep this. Any questions so far? As an example, we have mass equal to 3 kilograms, and we need to move it from y equal 5 to y equal 10. This is y1, this is y2. Okay? We need to move the mass to this direction. Not if I need to move this mass, I need to interact or do some work to lift it. But I'm asking about the gravity. The gravity in general, its work is downward. But if we force it to do its work upward in the opposite direction, then it will be a negative sign, and you will see that. So, compute the change in potential energy for this block. Okay. Now the work is equal to the weight downward, or mg, which is the weight downward, multiplied as a dot product by delta y. Delta y upward. How much theta between them? Again, we have the force downward and the weight, the displacement upward. So theta between them. This is the force, and this is the change in displacement. Theta between them is 180. So this will be equal to M3 multiplied by 9.8 plus simple when we take G is just 10 and complete our solution. And delta Y, it is 10 minus 5, which is 5. Multiplied by minus 1, this is minus. So it will be equal to minus 14, no, yes, 14.7 joules. This is the work, that work. Okay, what is the change? Now, what is delta U? U capital. As we know that the weight is equal to minus delta U. Okay, the weight is equal to negative 14.7, which is equal to negative the change in potential energy. So negative with negative is positive, then delta U is equal to 147 joules. Let me tell you something. The potential energy, if we release the object from, why you can see the yellow color. This is y equal to 5. This is y equal to 10. If I have, for example, glass, if I drop something from 5 meters, it's very high for it. Let's assume it block. If we drop this mass from 5 meters on this block, it will not smash it. But if we drop it from here, it will smash it. Or another example, if we put a glass, drop a stone on it from this height, it will not break it, right? But if we drop the stone from a higher place, it contains more energy, then it will break it, and we can't do it. So the mass in the high position have more energy than the mass at low position. So this energy depends on the altitude. This energy is stored in this object, in this mass, because of its position. Because of that, we call it potential energy. It is hidden, or what's the word? Or stored in that object in its position, and it depends on the position. We have M, G, Y. M is constant for the same object. G is constant. There is no difference between the two G's in this altitude near the surface of the ground, the surface of the air. But Y is different. This is delta Y. So the change in potential will depend on the change of altitude. In future lectures, we will see that if we have, for example, a spring, and we push this spring, we have two experiments. We push it a little amount, and in the next state, we push it more, where the potential energy is greater. Is it in the second or the first? We will see that. We have here more stored energy in this spring because we push it more than this one. So this is spring potential energy or elastic potential energy. It also depends on the displacement or the position of the system. Any questions? Okay, now we have energy, many types of energy. Now, energy, we see many kinds of energy. The first kind of it is the work, which is equal, as we know, to a force multiplied by delta displacement, delta x or delta y or something like that. This is the first kind of energy. We have another kind. It is the kinetic. As we see here, it is half v squared. We have now a third kind, which is potential. Potential in general, but now we are talking about due gravity. Yes. So now we have three kinds of energy. As I told you, the work is work. The kinetic energy, it is either linear kinetic energy like this, or rotational kinetic energy. We will take it later. Also, we have rotational work. I do now rotational work. I change the angle, not the displacement. But in this case, I change the displacement. Also, the potential energy has many kinds, as you see, due gravity. Also, if we have a spring, we have potential energy, due elastic forces. We have chemical potential energy as stored in the battery. It's chemical kinetic energy. We have electrical kinetic energy, magnetic, nuclear, two types of nuclear potential energy, and so on. We have heat also. I need to ask you something. In our system, maybe this room, or in nature, universe, there is an important relation between different kinds of energy. This relation is the conservation of these energies in the system. Okay? If we are talking about nature or universe, it's a big system, huge system. But we are in this room or in the lab, we have a subsystem, small system. We can assume that this subsystem inside the universe, we can apply the laws of physics inside our subsystem. The most important, one of the most important laws of physics is the energy conservation. Energy, now conservation of energy. Just like the conservation of mass. The mass cannot be created from nothing. Okay? We have 2 kilograms and 3 kilograms. It will be 5 kilograms. If we close this system, it will not change. If this system is open and someone come and steal half kilogram, then we will have this because we have a loss or waste in our conservation law. In our system, we can assume that this system is conserved. Okay? I am always do this example. We will do now an experiment. We have, this is our subsystem. And we have in this system an opportunity to have many kinds or types of energies. For example, we can have kinetic energy. We can have also gravity potential energy or due gravity. Also in this system we have due, for example, photonic. This is light. We have electric energy and light energy. We have mechanical energy due to the voice, what we hear in our system. Okay. What if we have also chemical potential energy? What if we have heat potential energy in our system? And at first, we give our system amount of energy, which is 100 joules. So how much the energy inside our system? It is 100. So our energy in this system is 100 joule. This 100 joule, maybe it will be, for example, 15 as a kinetic energy. Maybe there is a fan rotating. Due gravity, maybe there is an elevator. We have 20 joules. Photonic, maybe we have lights. We have 5 joules for the light. Chemical energy, maybe we have some charge. We need to charge some batteries or something like that. We have 30 joules. How much the total now? 15 and 20, 70. And we have 30. If I come and tell you we have heater or AACs with 25 joules, is this system conserved now? If we add them together, we have 50, 70, 95. So we have now, we need more 5 joules. We don't know where are they, right? Maybe these 5 joules are some work going from shape to shape. Maybe we have some work from this kinetic energy as a friction force with the rotational fan rotate, and it will there's a friction force between it and the axis. Then we have heat energy from kinetic energy will convert to heat energy as work. This work is equal to 5. When we add them all together, we will find that they are 100 joules. This system is conserved in our example, okay? And always it is. Okay, maybe some of our components of our system fall from up to down. Then our potential due gravity is come to be 18, for example. Where did the 2 joules go? They are go as work to be kinetic energy. Then kinetic energy will be 17. As we see, we have energies and we have a change between them. It's just like money. It is a change between energy, which is the work. The work is the way how the energy converted from shape to another shape. Is that clear? Any question about that? Okay. If there is a loss in our system, maybe we open the door. Then some from our heat will go up there, go out, and we have 20 and we have 5 most heat energy outside, right? But if we expand our system and make it all the college, for example, we can expand our system and we can see that our system is conserved again. Okay? But if we just have this system, then this system is not conserved. We will use this idea in example just to know that our energy is the same always. I need you to remember that, but we will do it again. We already compute the potential energy due to the spring. When we compute an example, I think, when we push that spring, but we compute that the force, the Hooke's force is equal to Kx, and we try to compute the work, which is the integration of f of x over dx for this system. This system is the spring system. This will be equal to the integration Kx dx. It will be equal to half Kx squared. This is the potential energy due to the spring. This is the elastic potential energy. We computed before using the integration, that previous lecture, using the integration method. But when we need to compute any example using springs, we will put it and use it again. So this is potential energy for a spring. Okay. Now we need to know more. Our class is mechanics. Okay, so we are not interested in chemical potential. We are not interested in photoelectric potential. Also not interested in heat. Sometimes we will deal with the work done by the friction force. It will convert to heat energy. But we will deal in general with mechanical energy. Mechanical energy. As we said, we have the work, we have the kinetic energy, we have the potential energy. Maybe it's due gravity, maybe it's due spring, or something like that. All of them are in mechanics course. So all of them, we can call them mechanical energy. For our system, in any example, we have total mechanical energy. In our example here, I suppose that this energy is equal to 100 joules. Okay? In our system, in any system, in our examples, we have total mechanical energy, and this mechanical energy should be conserved. Is that clear? If we start our example with 50 joules, then this 50 joules will stay with us to the end of our problem. But these 50 joules will convert from work to kinetic energy to potential energy, and so. If you look at this example, any questions so far? We have the same example, that building example. Its altitude, we have an object at this point. This point is 1, and this point is 4. We have 4 points. This is point 2. This is point 3. Here, y1 is equal to 60 meters, as we see. Y2 is equal to 40 meters. Y3 is equal to 20 meters. And Y4 is equal to 0. We have the mass is equal to 5 kilograms. We just have this. We have a free fall experiment. We have no friction force. Okay, we don't have any loss in our system. So our closed system is this. We can close it. Now we need to compute everything everywhere. What is everything everywhere? Previously we used U2 is equal to V1 plus 18. V2 squared is equal to V1 squared plus 2AGY, for example. We use the equations of motion, okay? Motionless. Now we will use the energy method. In general, at point number 1, we have mechanical energy. Mechanical energy. The mechanical energy, we can call it capital M. Okay. And the mechanical energy, as we see, it is the summation of these energies. In general, we will not put the work with it, but when we need, we will put it. The mechanical energy is in general, it is equal to kinetic energy plus potential energy. If you don't need to put E here, it is okay. I took it from my past, okay? So at point number 1, what is the mechanical energy? We don't know how much it is. What is the kinetic energy? It is 1 over 2. The mass is, how much the mass? It is 5. We can compute now. Plus the potential energy. I will write the formula at first. The mechanical energy is mechanical energy. The kinetic energy is 1 over 2 mass multiplied by V squared plus mgy. Okay? For the first point, the mechanical energy is unknown. Equal to have m, it is 5. How much the velocity, which is v1? v1 for a free falling object. How much the initial velocity? Always 0. Yes, it is, because this is the experiment. This is a free fall. V0 here or V initially is 0, but in projectile motion, V0 here, it is not 0. Or if I throw it down or like this. So this is 0 squared plus m is 5. I'm computing down the potential energy. G, it is 9.8. The altitude, y at the first point is 60. This will be equal to 0 plus how much? 2,940 joules. This is equal to mechanical energy at the first point. So the mechanical energy at the first point is equal to 2940 joules. Anyone now from us will tell this mechanical energy will stay the same in all the trajectory, right? Because we tell that from before mechanical energy is conserved. So what is the change in my system now? The change is in potential energy and in kinetic energy. We will see how. At point number 2, the mechanical energy at 2 is equal to half m, which is 5. I know the law now, but just I need to change the position. And I have V2 squared plus the potential energy at this point, which is m g y2. I will leave this as a kinetic energy at point number 2. Kinetic energy at point number 2. The mechanical energy is known now. I know it. It is constant. It is. That right? Yes. Which is equal to kinetic energy at point number 2 plus m is 5. G 9.8. Y it is 40 now. So is equal to kinetic energy at point number 2 plus how much this number is equal to? It is 1960 joules. Now I can find the kinetic energy. It's just this minus that. So I move this to here. Then minus 1960 is equal to kinetic energy at point number 2. This will be equal to 980 joules. This is the kinetic energy at this point. If I ask you find the velocity at point number 2, okay, kinetic energy is equal to 1/2 m. It is 5 m v2 squared, which is equal to 1/2 multiplied by 5, which is the mass, multiplied by v2 squared, which is equal to 980. Now you have just one unknown variable, which is v squared. You can find the velocity at this point. What about the third point? We will use the same. We just need to change the point. Now we are here. The mechanical energy at point number 3, it is the same. It is equal to kinetic energy at point number 3 plus the potential energy, which is m g y3. This energy is equal to it is the same. Okay, it is equal to kinetic energy at point number 3 plus m, it is 5. Y, it is 20. G, this 9.8 multiplied by 20. So kinetic energy will be equal to this minus that. Kinetic energy at point number 2 is equal to 2940 minus 1960. It will be equal to 900. No. This will be equal to 980. 980. This will be equal to 1960 joules. This is important. Now the kinetic energy, the potential energy gets lower and lower, but the potential energy comes bigger and bigger. Because that's right, the velocity of the falling body is higher and higher because its acceleration due to gravity, which is 9.8. its velocity now is bigger than before. Its kinetic energy now is bigger than before. That's right. It's 1960. There it was 980. The potential energy depends on the altitude, the height. Now, the height at the third point is less than the height here. Then the potential energy here is less than this. Finally, at point number 4, we need at point number 4. This is y4. This is not 29, 40 is equal to kinetic energy. Finally, at point number 4, plus m5g, it is 9.8. The altitude is 0. Now the potential energy here is at 0 level. So this is equal to 0. Now, this is 0. Now, the kinetic energy at the 4th point, or the finally, is equal to the total of the mechanical energy, which is 2940 joules, which is maximum kinetic energy. And at first point, we have maximum potential energy, when the kinetic energy was 0. After that, if I told you I need you to find that velocity finally, V4, this will be equal to half, the mass is 5, V4 squared. You can't find V finally, right? Any questions for that? Anybody need to repeat anything? Any questions online? You need to repeat anything? Can you hear me? Okay, now let us look at our example in a more comprehensive way. Here, we need the potential energy, here, the kinetic energy, here, the mechanical energy. How much the potential energy here? It was the maximum, which is 2940. Here, how much the kinetic energy? It was 0. The mechanical energy is this plus this. Here, the potential energy, it is 1960. All of them are in joules. We don't need to put the units in each cell. We need to just put it in the header cell, okay? Header row. Here, the kinetic energy, it is 980, yes, joules. How much the mechanical energy? Is the same. Again, we have the same values here because we have 60, 40, 20, 0 because the step is the same length. But if we change it, if we take it at 50, at 30, and 10, we will see different values. Okay. As we see now, we have a constant mechanical energy. If any one of you ask me, at first we have 29 40 joules as potential energy. How this energy convert to 980 kinetic energy in the second point? I will tell you that we have a work, mechanical work done. This work done in this way. This energy, potential energy, lose or lost a work. This work converted to kinetic energy, and the rest of the energy was 1960 joules. After that, the object, the mass, is able to do work again at this point. At this point, it is able to do a work and flow down to this point. It has its energy and it can also do another work. It will go to a next point. So we have another work. This is work 1, this is work 2, for example. And it still has another energy, potential energy at this point. At this point, it is also have or has energy and can do work. So it will then do, for example, if the mass is here and we have a table, we have force downward and a normal force upward, right? We have a work due gravity downward and another work due the normal force upward, and the total work is how much? We have the weight downward and we have the normal force upward. How much the total force? If we have a table like this, how much the total force vertically? 0, because the weight is the same as the normal force. How much the total work at this mass? How much the total work now? It is the work due gravity downward and the work due the normal force upward, and they are both the same. And the displacement is 0, then the work is 0. So if we have any surface stop the mass going down, then it will not be able to do any other work. But if we don't have this surface, then this mass is able to do another work and to lose its energy as a kinetic energy. To reach this point, at this point, its potential is equal to 0. For example, if we have air resistance, then during going down, there is a heat energy. For example, 10 joules for each step. Then the kinetic energy plus the heat energy due resistance will be equal to the initial energy. But in our example, we don't have any rules. I'll tell you something. If we have the initial energy is, and this energy will be converted to 900 joules as kinetic. This is kinetic. This is potential. And then the potential will be how much? 1960. Right? We don't have any rules. But if we have air friction force and we have some loss of energy, for example, 10 joules as heat because of the friction force, then the kinetic energy will be 1970, not 1980. Because if you need to add this to this, it will be, if you add this to this, finally it will be. Now the energy is not conserved. We need to add it to it that work due friction force. then it will be conserved. This work converted to a heat potential energy. Heat potential energy. It's potential energy. Now we don't have any waste in our energy. We just have work to convert from potential to kinetic. Is this understood? If you use this idea, the solving example, the simple idea, you will solve all the examples or the problems. Okay? Now, if we need to use the graph, because in general we have energy graph. If we have the energy on the y-axis and the position on the x-axis, it is y in our example, or the velocity or the time, central ones of our experiment between our points. We have point number 0. The first point is 1. Point number 2. Point number 3. And point number 4. If you ask me about the displacement at each point, it is 60, 40, 20, and so on. If you ask me about the velocity, I need to compute the velocity from the kinetic energy. And also I can compute the time. The energy, we have 3 kinds of energy. 3 kinds of energy. You can see that. We have 3 colors, orange and yellow and green. How will you we have the mechanical energy, it is constant, always, right? This mechanical energy is equal to M2940. All of them are in joules, right? It is equal, it is almost constant. Now we have the potential energy. At point number 1, the potential energy was maximum. Then it becomes, at point number 2, the potential energy is 1960. This is 1960. At point number 3, the potential energy is 900, how much? 80. At point number 4, it is 0. This is 0. What about the kinetic energy? The kinetic energy at point number 1. So this is the potential energy, which is U in yellow. This graph is for mechanical energy, for potential energy, for kinetic energy. All of them together. Now, the kinetic energy was 0, then it becomes to be, because some work is done by the gravity, then the kinetic energy is 980, then kinetic energy becomes to be 1960, then finally kinetic energy be the maximum. So we have 2 graphs. If one of you told me that the kinetic energy in our system is 2000, that is wrong. ask you to compute not 3000, I'm sorry. If I told you to compute the kinetic energy and you told me it is 3000. 3000 is more than this maximum amount of energy. Then you have some wrong. You did it in your calculation. Because the conservation of energy, we can't create, just God can do that. We can't create energy from nothing, right? So this is wrong. For kinetic or for potential. So we have this graph for kinetic energy and this graph for potential energy. If you add this graph to this graph, you will find the total mechanical energy. If you add, for example, this to this, both of them will be how much? The total mechanical energy, right? So the total mechanical energy is always constant. If we have now, if you look to this graph, you can know everything about the system. In the future, we will see that we have many graphs. I will remove this now. And I will draw another graph. Here we have the energy. Here we have everything, even y or x or the velocity or the time. But we have 3 types of energies. If you need, I can put more. I can put the friction force energy. I can put the spring energy, rotational energy, any kind of energy, I can put it in this graph. Now, I will use that my mechanical energy is constant, which is equal to 100 joules for simplicity. And my potential energy, like this. And I have this. This is 100, as I told you. This is halfway, it is 50. This is 25. This is 75, and so on. If I ask you, for example, to find this is point P. How would the potential, this potential energy? Who can tell me where is the kinetic energy? Right. I will show you something. This is the potential energy, right? How about the kinetic energy? It is the rest, right? So if I do this, then simply this is kinetic energy and this is potential energy. If we add them together, they will give us the total mechanical energy. If you need to graph this, you need just to reflect it like this. Let me see this. Is it the same? So this is the kinetic energy. This is the kinetic energy. What if I ask you, how is the kinetic energy at this point? You can approximate. This point is approximately 35. For example, this is 35. How much kinetic energy then? Who can tell me? Hello? I can repeat if anybody has any complex rate, I will difficult thing I will repeat. Do you need me to repeat it? Just shake your head. It's okay. Look, as we see from before here, the mechanical energy is constant. If we need to graph any constant function, it is just a horizontal line, right? This is the mechanical energy, total mechanical energy. It is constant. Now, this mechanical energy is composed of two kinds of energies. The orange one is the kinetic energy, the yellow one is the potential energy. If I pick any 2 points, for example, this and this, and add them together, add their quantities together, then I will find the final mechanical energy. If I add 980 to 1960, I will find 2940. Okay? Now, another way, the area under the potential energy plus the area under the kinetic energy, add them together, it will give you the area under the mechanical energy, total mechanical energy. This is mechanical energy. Now, I have the orange graph is the potential energy. If I pick any point at this graph, and this point will tell me how much the potential energy now at this point. Okay, what is the rest of my energy to reach the mechanical energy? It is this amount. So this is potential. This is mechanical. So between the rest of the potential to this one is the kinetic energy. When I add potential energy to kinetic energy, I will reach the mechanical energy, total mechanical energy. At each point, if I tell you this is 25, how much of kinetic energy? It is 75, because 75 plus 25, 100. Okay? This is about graphs. It is simple. The mechanical energy is constant. We don't have any rules in our energy. If we have rules, then it will be 100, 90, 80, and so on, and will come decreasing to reach zero, to lose when it is lose all of its energy. But in general, it is simple like this. If I ask you what is the maximum kinetic energy in this graph, you will tell me that at t equal to 0, I have maximum kinetic energy, which is 100 joule. But from this period, during this period, what is the maximum kinetic energy? It is at the minimum potential energy. For example, it is 18 potential energy. Then the kinetic energy at this point, 100 minus 18, which is 82 joules. It is the maximum potential energy in this period. Is that clear? At any point we can find the altitude. If I told you about this graph, this is U gravity, and the kinetic energy is equal to half mv squared. At each point also I can ask you how much y, how much the altitude of that point at that point. You can use this mgy. At this point, the potential energy is 18. G is known. I can can give you that M is equal to 10 kilograms, for example, or it's given, then you can find out. If you know the kinetic energy, the mass is known, then you can find the velocity. Just multiply by 2, it will be 2k. Divided over m, it will be 2k over m. Take the square root, it will be 2k over m. The root of it will give me the velocity at that point. Maybe it is positive, maybe it is negative. If it is positive, I need to look to my system. For example, in our system here, we have a building, and we have positive y and negative y. The velocity is downward. So which velocity you will pick? The negative one, because you are going to negative direction. Any questions so far? Online, any questions? That's all for today, and we will come to we will do in the next week some examples using the spring and friction force. And keep in your mind that the energy is the same. Maybe we will lose it due to friction force. You have, I think, homework for the previous lecture chapter. If you need more time to do it, it is okay. And thank you for that. Any questions online?